draw a line through your arrow. That is going to help split reactants and products. Then you just list the number of atoms based on their formula. So Cl2 tells you that there are 2 chlorines. H2O tells you that there's 2 hydrogens and 1 oxygen. And that is all on the reactant side, so on the left. Then you look on the opposite side of the arrow. You see HCl, so that tells you that there's 1 hydrogen and 2 chlorines. Or sorry, 1 hydrogen and 1 chlorine. And that there is 2 oxygens in O2. Remember that I write OXY. You can just write a 0 or an O, but it looks like a 0 to me, so because I get all confused. Now, when you look at this, do you notice that nothing is balanced? I've got 2 chlorines, 1 chlorine, 2 hydrogens, 1 hydrogen, 1 oxygen, 2 oxygen. But they're all what I call simple. Simple means they're only in one place on either side. So it's really your choice. You can pick whichever one you want to balance first. So what'd you balance first? So you did hydrogen first. So it doesn't matter, like it really doesn't if they're just all found in single places, meaning only in one molecule on either side. Just pick one. So someone said hydrogen first. So I have 2 hydrogens on the left, 1 hydrogen on the right. So I know I'm going to have to increase the hydrogens to have a total of 2. So what do I have to put in front of HCl? So I got to put in 2 as the coefficient in front of HCl, because remember that's going to multiply the number of hydrogens and the number of chlorines on this side by 2. So now I have 2 hydrogens and I have 2 chlorines. So you look at it and you're like, oh, good. Look, I balanced my chlorines. Okay, I balanced the hydrogens, 2 of each. Now I have 2 chlorines of each. So the only thing I have left to balance is the oxygen. So in order to balance the oxygen, which side do I need to change? The left or the right? The left. It's always the one that's lower is the one that I'm going to need to change. So if I have 1 oxygen on the left, 2 oxygens on the right, what coefficient do I need to put in front of H2O? I have to put a 2. Okay. Now remember that's 2 times the water. So that means that I'm going to have to multiply the hydrogen and the oxygen of water times 2. So that'll now give me 4 hydrogens and 2 oxygens. And so some people stop there and they're like, well, wait, now I just messed up my hydrogens. That's okay. Okay. The goal is that eventually you're going to have to continue to change those coefficients. Any number you put on the line in front multiplies all of the atoms that's in that element or compound, whatever that molecule is, by the number that's on the coefficient. So this 2 tells me I have to multiply the hydrogen and the oxygen by 2. This 2 over here tells me I have to multiply the hydrogen and the chlorine by 2. So am I done? No, because what did I do? I unbalanced what's not balanced now. Hydrogens. Does everybody see I have 4 hydrogens on the left and only 2 hydrogens on the right? So which one do I need to change? The one on the right, the lower one. So if I have 2 hydrogens with that 2 in front, what will I have to multiply this by to make 4? 2 more. So I'm going to have to say times 2, times 2, times 2. That's going to give me 4 hydrogens, and that's going to give me 4 chlorines. So now my oxygens are balanced with 2 and 2. My hydrogens are balanced 4 and 4. But what about my chlorines? No, I messed up the chlorines. So how do I balance the chlorines? Which side? I'm going to have to change the left side, right? So chlorines 2 on the left, 4 on the right. So I know I'm going to have to increase the smaller. What do I have to multiply the chlorines by to have a total of 4? Multiply it times 2 more. So I'm going to have to put a 2 in front of the chlorine. And remember that that means that I multiply that chlorine times 2, and that will give me a total of 4 chlorines. So now when you look, are they balanced? Do I have 4 chlorines on both sides, 4 hydrogens on both sides, 2 oxygens on both sides? Okay, so now looking at the equation where you have this 2 times 2, you can just change this to a 4. Okay, so whatever, if you have to go back and multiply a number again, that's okay. When you get done, the total numbers that you have to multiply, you just figure out what their product is. So the oxygen has nothing. So what actually belongs on that line? a 1. Because what that means is I only needed 1 oxygen formed in order to have a balanced equation. So this, if you end up with a blank, that doesn't mean that there's no oxygen. It just means I only needed 1. Just having those 2 oxygens on the right side of the equation was enough when I did the balancing. I didn't have to change it. So you won't have to change every single coefficient. You're looking to balance the total number of atoms on each side, and don't be bothered if you have to go back and actually multiply an element by a number again, like we had to do with the hydrogen and the chlorine on the right side. But when you get all done, then just make sure that you put the total product number in front of each of them for the balanced equation. Okay? So looking at this one can be a bit of a challenge. One, it's got oxygen in two places on the product side. So that means I'm going to do that one last, right? I call those the more complicated ones. So carbon is only found in one place on either side. So I can balance that one. Hydrogen is only found on one place in either side. I can balance that one first. Do the simple ones found only in one place on either side first, then worry about the oxygens. So which one would you like to balance first? Carbon or hydrogen? Okay, so balance the carbon. So left, I have 2 carbons. Right, I have 1 carbon. So which side do I change? The right side. So I have to put a 2 in front of CO2 because I need a total of 2 carbons. But remember, that is going to multiply everything in that molecule, the carbon and that oxygen, multiplied by 2. So I have 2 carbons and 4 oxygens now over on the product side. So the next one to balance is the hydrogens. So I have 6 hydrogens on the left. I have 2 hydrogens on the right. So which side do I change? The right. How do I end up having a total of 6? Multiply it by 3. And remember, that's going to multiply the hydrogens and the oxygen in the water by 3. That'll give me 6 hydrogens, 3 oxygens. So notice in doing that, I didn't mess up my carbons. I'm still 2 and 2. My hydrogens are now balanced with 6 and 6. So now my oxygens, over on the left side, I have 2. Over on the right side, what is my total number? 7. Okay, so in this, what would I need to put in front of the oxygen in order to make 7? What times 2 is 7? A what? So if I put a 3.5, this is sort of an easy, if you have this, if you get done and it's the only things left to balance are these last 2, and you get finished and you're like, well, I have an odd number and an even number. 2 ways you can do this. You can either do the least common number they both go into, which would be 14, or you could look at it and say, well, if I have a 2 and a 7, 3.5 would actually make this balanced. Because if I took this oxygen and multiplied it by 3.5, I'd have 7 oxygens, and these would be balanced. So the rule, though, is you have to have the simplest whole number ratio. So if I got done, I'd say, well, I didn't have to change that last one, so this would be a 1. So it would be 1 C2H6 plus 3.5 O2s would make 3 H2Os and 2 CO2s. But the rule is I have to have only whole numbers. So what would I have to multiply all of these by to make them whole numbers? If I multiplied everything times 2, so if I said this times 2, that would make this a 2. 3.5 times 2 would be a 7. 3 times 2, 6. And then 2 times 2, 4. So you want the simplest whole number ratio. The other way that you could do this when you get to the oxygens is if you see there's a 2 and a 7, the smallest number they both go into is a 14. So you would have to balance your oxygens, making both sides 14, and then you just end up going back and balancing that first element, the C2H6. So either way, I'd end up with the exact same number, okay? Because it's basically would end up doubling everything else except fixing that oxygen. Okay, so this is one, especially if you have one where oxygen is the last group that you have to balance, and you have an odd and an even number. If you have an odd and an even number, then you can figure out how many of the even numbers to make the odd, and then just double everything. So this you're going to see, this is pretty typical with oxygen as the last. That's really the last to balance. You can do it in this way, or you can do the smallest number they both go into. Both of them would have ended up giving you the exact same answer. Sometimes when you look at problems like this one, so NH4Cl plus AgNO3 makes NH4NO3 plus AgCl2. So you look, or AgCl. So you look at this and you're like, ooh, there's an awful lot of atoms in this. Don't let that bother you. Just list them. Just go through and list them individually. So remember, this whole molecule, I have 1 nitrogen, 4 hydrogens, 1 chlorine. I also have 1 silver, 1 Ag, 1 N, and then 3 oxygens. So here's the grouping. Is I have nitrogens in 2 places on this side. Over on the opposite side, I have NH4NO3. So there's 2 nitrogens in that one molecule, 4 hydrogens, 3 oxygens, 1 silver, Ag, and 1 chlorine. So when you go through and look at these, how many nitrogens on each side? 2. How many hydrogens? How many chlorines? How many silver? And how many oxygen? So it is already balanced. So if it's already balanced, you don't have to do anything. There would be that they're just ones. Okay? That they already exist with an equal number of nitrogens, hydrogens, chlorines, silvers, and oxygens on both sides. So there are occasions where it's already going to be balanced. So don't be like, well, I have to change something. You don't have to change anything if the numbers, the total number of each atom on both sides is already the same. So remember that in your handout, I'm not 100% sure if I have one. No. So you've got that handout that's stapled. The one that has the periodic table is the last page. The very first page looks like a unit conversion page, which we're going to do next. So the middle page, that is front and back, all balancing equations. And all of that, the keys for that are posted in Moodle. So you need to go to the Exam 1 module. If you go to the Exam 1 module, you'll find the examples as well as the keys that are posted there. So if you practice these, feel like, okay, I think I'm getting these, you can actually go and check yourself. These, I'll just tell you, there's usually 10 to 15 points on your first exam of balancing equations. So if this is something where you're like, I'm not getting this, 2 things you can do. 1, you know that you can always rewatch those lectures. I post the video lectures. I'm recording this lecture now. It's posted in the Exam 1 module. I also have another sort of short tutorial, about 15 minutes, that I called Math Review. And I also do balancing equations in the Math Review just to sort of give you more hints. Sometimes it's just a matter of like looking at it from different ways until it like clicks. You can also look at your e-text. Same information is covered in Chapter 1. So those are all different ways or different places that you can go through. Try to follow the steps, follow the path that you need to do in solving those. And if you still are stuck, come and see me during my office hours. I still don't have Abigail's tutoring. I will try to make sure that I have them by Thursday so that they're posted. So I have Abigail Macedo is our student tutor. She's available 5 hours a week in 7213, which is upstairs, kind of the middle of the hallway. It's sort of our tutoring center that we have for science. She took this class last semester, so it's pretty fresh in her head. And I will tell you, she had a 98 average in my class. Okay? So she like gets it. And so she has seen all of this. So anything that you go to her with, she'll be like, oh, let me explain this. Like, she's really good at it. She enjoys this. And she was really, I was really pleased that she was able to fit it into her schedule, because she would be a really good asset, especially if you just have some questions. Like I said, you can always find me during my office hours, but I'll find her 5 other hours to help. I think it'll help as well as an option. Okay, so we're moving on. The whole middle of this Chapter 1, the beginning was all about like, so basic definitions, classification of matter, the periodic table, the elements and symbols you need to know, and then finished up all of that with physical, chemical changes, and then balancing. That's kind of like that first part. And I would say chapter 1, chapter 3, those are big chapters. The rest of the chapters are sort of more moderate, but this one I feel like is a big chapter because it's like, do you remember doing this? That's what most of these are. Do you remember doing this in another class somewhere in your life? And so for some of you, it's like, yeah, I just had all this. For other people, it's like, oh no, it's been a long time since I've done this. So metric. The metric system is how we count in chemistry. We don't use English units. We don't measure things in inches. We don't measure things in pounds. We don't talk about miles. We don't talk about quarts. Everything is done in metric, but metric is actually easier. Metric, everything is based on powers of 10. So instead of having to remember all of those numbers to change things, all you have to do is move your decimal place. So your number doesn't really, the actual number units don't change, but the size of the units end up changing. So good example. For me, I know that there are 12 inches in a foot. I know that there are 3 feet in a yard. But you have to remember that 12. You have to remember that 3. When you go from centimeters to meters, you only have to move a decimal place, 2 places. To go from meters to kilometers or kilometers, it's just a matter of moving decimal places. I, for the life of me, cannot remember how many yards are in a mile. It's like 1,600 something. But like I can never, whenever I have to look, I have to go back and look that number up. I cannot just randomly remember that number. In metric, it's not that way. In metric, you have what they call base units. The base unit for mass is the gram. Okay? So the gram, a gram is a little bit bigger than a pinch of salt. Okay? Maybe like a 1/4 teaspoon of salt is about what a gram is. It's a pretty small measurement of mass. When we talk about people's weights, instead of grams, we typically use kilograms. So if you are going to go into any kind of health science and there's any kind of medication, you don't typically give it to the patients in terms of their pound size. You have to convert that to kilograms because the medication dosages are always like milligrams per kilogram, grams per kilogram, milliliters per kilogram. It's always based on their body weight in kilograms. So that kilo is what they call a prefix. So we use the gram as the base unit, and then the kilogram, the kilo, becomes the prefix to indicate a size that is larger than this little 1/4 teaspoon mass of salt. Liter. This, fortunately, is the one that people are the most familiar with because everybody has seen a 2-liter bottle of soda. So when the 2-liter bottles of soda came out, everybody was like, oh, now I know what a liter is. So I know what a liter is because I just imagine, okay, that's half of one of those bottles. So liter is a lot like a quart. Okay, so a liter can be indicated larger or smaller by using the prefix. So we can have a milliliter. So a milliliter is a very small amount, or you could have centiliters, we could have deciliters, we could have kiloliters. The third one is length. So we have weight or mass, we have volume, the amount of space something takes up, and then we have length. So length, instead of it being a yard, we have a meter. And a meter is about 2 3/4 inches longer than a yard is. So you've seen a yardstick, so a meter stick is just a little bit longer. So that is the base unit. So that's one that is a little more sort of familiar, or you can think of it in terms of it's close to a yard in size. But then I can have little measurements because I can add the prefix. So a centimeter is just under 1/2 inch. So centi means that it's a smaller size. There's really only 5 prefixes that I think you need to know. Okay, 5 prefixes. If you can remember these 5 prefixes, then you can remember the size of any unit for any type of metric measurement, whether we're talking about mass, length, or volume, grams, liters, or meters. If we add these 5, and here's the first one, and here are the other 4. I am not very concerned with giga because you will almost never use that in health sciences, or mega because they're humongous units compared to the base unit. I'm also not all that concerned about nano, because although you might give micro, which is really small, nano is 1,000 times smaller than that. So we don't use those all that often. So it's really these 5. These are the only 5 that you need to commit to memory. The first one, kilo. So kilo, it's a little k is its abbreviation. So having a prefix kilo in front of a base unit means that it is 1,000 times larger than the base unit. And base unit is a meter, liter, or a gram. So the base unit is just a unit of length, volume, or mass, just with no prefix. So meter, liter, or gram would be considered the base unit. So if I have 1 kilometer, that is going to be equal to 1,000 meters. So it takes 1,000 of these to make a kilometer, and a kilometer, just by length, is about 6/10 of a mile. So if you think 1,000 of these is just over a half a mile in length. So kilo is big. It's like measuring a mile compared to an inch. So kilo is a large measurement. It takes 1,000 base units to make a kilo. So that means if I have 1 kilogram, that is equal to 1,000 grams. If I have 1 kiloliter, then that is equal to 1,000 liters. So whenever I see kilo in a unit conversion, kilo is bigger. Kilo gets a 1, and the base unit will have 1,000 in front of it. So notice it's the same for all of them. It doesn't matter if I'm measuring volume, length, or mass. That's not the case in English. In English, it's different when you're talking about pounds versus volume in quarts, gallons, or pints, or cups. Like there's so many different ones. And it's even still different if you're talking about length, where you've got inches, feet. They're all different unit values, and they all have different size differences to them. Here it's always the same. The other 4, on the other hand, are all smaller. Deci, centi, milli, and micro are the other 4. They're all smaller than the base unit. Deci, D-E-C-I, a little d, it is 10 times smaller than the base unit. So whenever I have to do a unit conversion that includes deci, I will have a 10 in front of the term that has the deci. So it takes 10 decimeters to make 1 meter, 10 decigrams to make 1 gram, 10 deciliters to make 1 liter. So see how the deci always gets the 10 in front, and the base unit is a 1. These other ones followed the same. So centi is a little c. Centi is 100 times smaller than the base unit. That means it takes 100 centis to make a base unit. So I would have 100 centimeters to make a meter, 100 centigrams to make a gram, 100 centiliters to make a liter. So centi will always have 100 in front. Deci always has a 10 in front. Milli is the little m, which sometimes throws people because the other little m is meter. So when you see mm, that's millimeter. But if you see cm, that's centimeter. So if you have 2 letters in your unit value, if the first letter is an m, a little m, it's the milli. If the second letter is a little m, then that's meter, which is like, why couldn't they have just, there's 26 letters in the alphabet, but no, they've got to use all the same letters, but no. So that is the sort of the challenge to remember. The first, if you have 2 letters in your measurement abbreviation, the first is always the prefix. And if it's an M, it's milli. The second is always the unit. It's either going to be a C, a G, or sorry, not a C. It'll either be an M, a G, or an L. It's either going to be meters, grams, or liters. That is the measurement type or the unit value. So milli's 1,000 times smaller. So this means that it is going to take 1,000 millimeters to make 1 meter. And if you've seen a ruler, metric rulers have those small little dash marks. Those are millimeters. So those are about the width of like 3 hairs set side by side. So that's that millimeter size. It takes 1,000 of those to make 1 meter stick. 1,000 milligrams to make 1 gram, and 1,000 milliliters to make a liter. The last one. So the last one they called micro. And again, keeping the M, but they ran out of M's because see, mega got the capital M, milli got the little m. They also use little m for meter. So when they come up to micro with another M to give it a unit value, a sort of abbreviation, micro is what they call the mu. It is a Greek symbol. It looks like a U with a foot kind of hanging down on the front. It is a Greek symbol called mu. So don't let that throw you. It looks kind of like a U, but typically the little piece sticks down on the front. That is micro, and it is 1,000,000 times smaller. I always think of microscopic. Things that are micro are really, really little. So like looking at microorganisms, you have to have a microscope because these are very small amounts that you're measuring. They are 1,000,000 times smaller than whatever base unit we're talking about. Just make sure that you double check. You put 6 zeros in your calculator when you do this. So it means it is going to take 1, 2, 3, 4, 5, 6, 1,000,000 micrometers to make 1 meter. So these measurements you can't actually see with the naked eye. This is what you can see when you look in a microscope, is you can actually see micrometers, which they also call microns. 1,000,000, 1, 2, 3, 4, 5, 6 micrograms to be able to make a gram. So remember I said, like, if you weighed out about just under a 1/4 teaspoon of salt, that would be 1 gram. So you would have to take and split that into 1,000,000 little pieces in order to measure a microgram. So it's pretty small. Micro is a really small unit. 1,000,000 microliters to make 1 liter. So a microliter is usually, it's like about a 20th of a drop. So it's like teeny tiny volume amounts. Anytime you see micro, 1,000,000 is going to go in front of that unit. Anytime you see milli, 1,000 goes in front of the unit. Centi would always get 100, deci gets a 10. So the ones, these 4 that are smaller, the prefix unit will always get a number value more than 1. Kilo is the oddball. So just notice that kilo is different. Ooh. Kilo, anytime you have to convert and use kilo, kilo gets a 1. And the base unit gets 1,000 because kilo is a really big measurement. A large amount, like kilograms, almost 1/2 of a pound, compared to a gram, which is like a 1/4 teaspoon in mass. So using these, we can convert from one unit to the next by setting up what they call a conversion factor. So you saw on the previous page that I was saying they're equal. So in this, like with deci, 10 decimeters is 1 meter. So they're equal to each other. So that means that I could put them on top of each other in either way because they're saying the same thing. They're just using different measurement values. So like I said, you can measure things in mass, volume, or length, and all you have to remember are what these 5 prefixes mean compared to the base unit. And the base unit is just the unit without a prefix. So the base unit is either gram, meter, or liter, depending on what kind of measurement you're talking about. So in here, if I want to measure, if I want to convert, or I'm going to use decigrams and grams, I know that there are 10 decigrams. I said 10 decigrams is equal to 1 gram. They're equal. So I can put them over one another and they mean the same value. So I can use this to be able to go from decigrams to grams or from grams to decigrams. And another way to think of it is everybody agrees these are saying the same things. So if you have 12 eggs or you have a dozen eggs, that's talking about the same amount, but notice those numbers are different. So 12 eggs is talking about the individual units. A dozen is talking about sort of a whole different value or size. Same thing with this. So I can set decigrams and grams one over the other as long as I'm using that conversion factor. This can allow me to convert from one form to another. So let's say that you have 250 milliliters and you want to know how many liters that is. Because I have liters as one of my problems, I can do this in a single step. 250 milliliters equals how many liters? And here's this way that you're always going to set it up. So you always write what you know first. So what do I know? 250 milliliters. So 250 milliliters, then put a times and draw a line. Okay, you put the number you know times in a line. So this line is what's going to allow me to put my conversion unit there. So what do you know when I put a unit in the numerator and the unit in the denominator? What will they do? They're going to cancel each other out. So if milliliters is what I'm starting with, then I know milliliters is what needs to go on the bottom because I want milliliters and milliliters to cancel. That's the given unit. That's my starting unit. It's always going to go on the bottom in the first step, whether you're doing a one-step or two-step conversion. It's always going to go on the bottom in the first step. What's going to go on top? I want my desired unit. So what's the unit for my answer? Liters. So I'm going to put liters on top. Okay, so I always write down what I'm given, times in a line. Then I assign the units. What unit goes on the bottom, what unit goes on the top. Now, here's the part that you have to remember. Milli, what goes in front of milli? 1,000. Flip back to your page before if you can't remember. Remember that milli gets the 1,000. So milli gets the 1,000. The base unit gets a 1. Because it is 1,000 milliliters is equal to 1 liter. So this is my unit conversion number. Now I just do the math. So milliliters and milliliters cancel. See, my answer is now in liters. So I'm going to take 250. You can multiply it times 1 because you do everything across the top. But anytime you multiply or divide by 1, what happens? Stays exactly the same. So really you can ignore the 1. So this is saying 250 divided by 1,000. So what'd you get? 0.25. So if you can remember that when you see kilo, kilo gets a 1, base unit gets the 1,000. When you see deci, deci gets a 10, base unit gets a 1. Centi, centi gets 100, base unit gets a 1. Milli gets 1,000, base unit gets a 1. Micro gets 1,000,000, base unit gets a 1. If you can remember those 5, and I just went ahead and listed them up on top. If you can remember those 5, you can convert any metric value. Those are the only 5 things that you really need to be familiar with and use those to set up a unit conversion. So here is 24 milliliters. That looks familiar. So 24 milliliters, I want to convert it to liters. So what do I put down first? What's my given unit? 24 milliliters. 24 ml. Second thing, times in a line. What unit do I put on the bottom? ml. And it should be a little m, capital L, but I'm really bad about writing it in kind of cursive-y. So that's what that ml should be should look like this. You'll see me do it just because it's a bad habit. Okay, what goes on top? Liter. Okay, so when you see milli, what goes in front? 1,000. Up here, anytime you see milli, 1,000 goes in front of milli, liters gets the 1. So here again, milliliters and milliliters will cancel. 24 divided by 1,000. 0.024. What about this one? 97.1 grams is how many kilograms? What do you put down first? 97.1 grams. And then times in a line. What unit am I going to put on the bottom? Grams. Whatever you're given, put that on the bottom first. And now, what do I put on top? Kilograms. Now, what do I have to remember? Kilo gets... No. Kilo is huge. Kilo, the biggest unit, gets the 1. Kilo is huge. It gets the 1. What's gram? 1,000. Right? So see how milli gets the 1,000 when it's milli and with the base unit, but kilo always gets a 1 because kilo's the bigger unit. The biggest unit is the one that gets a 1. Centi, deci, milli, micro, they're all smaller units. That is why they have 10, 100, 1,000, a million. But kilo is a bigger unit, so it gets the 1. Okay? So, units cancel. So grams and grams cancel. When you do this math, 97.1 divided by 1,000 is? And you do not round when you do unit conversions. You just keep all the numbers. You don't round or drop any off. You got to keep those. 125,000 micrometers is how many meters? So in this one, put down what you're given. So remember that funny little U is micro. Next thing you put in, times in a line. What goes on the bottom? Micrometers goes on the bottom. What unit on top? Meters. So then what numbers do you put in? A million. Micro gets the million, which is a 1 with 6 zeros after it. Meters gets the 1. The base unit is bigger, so it gets the 1. Micro is smaller, it gets the million. Now when I do this math, micrometers and micrometers will cancel. 125,000 divided by a million ends up being 0.125. So in all of these cases, one of my units is a base unit. And the first one, liters, is my base, is in there. Second one, grams, is in there. Third one, meters, is in there. So there's a base unit as one of my unit values in the problem. Then I only ever have to do a single step. I just have to make the relationship between what I'm given and what the desired unit is. They're always going to have an equivalent because there's the base unit is in one of them. But sometimes I end up with a problem where both of my units have prefixes. So you see in this one, I have decigrams and milligrams. So one unit is deci, one unit is milli. So in doing this, I want you to do this in 2 steps. So if you do this, if you see 2 letters in your unit, then you know it's a prefix. If you only had 1, then you know it's a base unit. If it's just an M, you know it's meters. Just an L, you know it's liters. Just a G, you know it's grams. But if I see DG, then I know that's decigrams. If I see MG, I know that's milligrams. So I have here decigrams and milligrams. So when we learn those 5, I learned how deci is related to a base unit, and I learned how milli is related to a base unit. But we don't really talk about how they're related to each other. So for this, go from the prefixed unit you start with, go to the base unit, and then from there, go to your answer. So you're going to just do it in 2 steps, and you still don't have to remember anything except those 5 things that we talked about. So here's the steps. And so when I say 2 steps, it just means I'm going to set this up, and I'm going to have 2 conversion factors. So what am I given? 4 decigrams, that's where I'm starting. 4 DG, then you go times and a line. What unit will go on the bottom? Decigrams, because that always, what you start with, always goes on the bottom in the first step. But since these are two prefixed units, I need to go to the base unit first. So what's the base unit? Grams. When you see deci, deci gets a 10. Grams gets the 1 because deci is 10 times smaller. 10 decis makes a base unit. But I'm not done. I just did this step. Now I need to do this step. So the second step times and another line. What goes on the bottom this time? What do I got to get rid of? Grams. So see, whatever I have at the top in this step now goes on the bottom in the next step. And my answer can go on the top, which is milligrams. So I'm just doing it like 2 unit conversions. I'm just splitting them. Okay, whenever you see milli, what goes in front? 1,000. Like the millennium, milli gets 1,000. The base unit gets a 1. Deci, centi, milli, micro, the base unit always gets a 1, and they're either going to be a 10, 100,000, or a million. So notice when I do this math, the decigrams and decigrams will cancel. Grams and grams will cancel. My answer is in milligrams. Now doing the math. Multiply everything across the top. So that is 4 times 1. Remember, that doesn't do anything. So just 4 times 1,000, and then divide by each thing in the bottom. So it'd be 4 times 1,000 divided by 10. And your answer is 400. So let's set up the next one. So 24 kiloliters is how many deciliters? And that really, they should be capital L's. Thought I fixed all those. Okay, 24, when you see kilo, that's a prefixed unit. And then you look and you see deci, that's a prefixed unit. So if I have prefixed units on both sides, then I know I got to do it in 2 steps. So what am I going to convert to first? I'm going to go from kiloliters to liters, and then I can go from liters to deciliters. Go to your answer. So I'm just going to set this up with 2 unit conversions. What number do I start with? 24 KL times in a line. What unit goes on the bottom? Kiloliters on the bottom. What goes on top? Liters. And notice that I assign the units first. And don't put the numbers first. First put the units, because then that way you make sure you put the right numbers in the right place. Kilo gets a 1 because kilo's the biggest. So kilo gets a 1, which means liters is the 1,000. So there's step 1. So I just did step 1. So I'll change colors when you do step 2. Times and a line, because I got to get rid of what in the second step? Liters. So liters goes on the bottom. So what was on the top now goes on the bottom. And my final answer that I want is in deciliters. So I put the units first. Now tell me, when I see deci, what do I put? 10. Deci needs 10 in front. Liters is the bigger unit, so it gets the 1. So when I look, kiloliters cancel, liters cancel. My answer's in deciliters. And when you do the math here, 24 times 1,000 times 10. Divided by 1, divided by 1, doesn't change anything, so there's nothing that you have to divide it by. 24 times 1,000 times 10 is 240,000. Okay, try the next one. See if you can do this one. And it's really just a matter of remembering, okay, what is centi, what is micro, what is milli, what is deci, what is kilo? Like, how do I set up those unit conversions? Okay, so what'd you put down first? Micrograms. That funny little U is a micro, so you could say micrograms. So you put that down first, times in a line. Everybody put micrograms on the bottom, grams on top. Micro gets a million. That's a 1 with 6 zeros. I do see that. I see people put the wrong number of zeros when they take the test. They're just going fast. So stop, take a breath, count your zeros. Okay, that's always like just to check yourself. Grams goes on the top. Then the second step, grams goes on the bottom, centigrams goes on the top. What number do I put in front of centi? 100. Deci is 10, centi's 100. Grams gets because it's bigger. Okay, so the bigger unit gets the 1, smaller unit has to have a certain number, but it's always based on 10. So now micrograms, micrograms, grams, and grams will cancel. So I have to take 97,123 times 100, divide it by 1,000,000. I always go and multiply everything across the top, and then I divide by each thing in the bottom. And so in doing this, what did you end up with? 9.7123. Everybody get that? Okay? This is as hard as that gets. Okay? It doesn't get any harder in doing unit conversions than this. One step, if we're talking about a base unit as one of the values, so if you have just grams or liters or meters only as one of your unit values, you can do it in a single step. But if you have 2 prefixed units, then just do it in 2 steps. But you still don't have to remember anything more than what I've got written up at the top. You just have to remember what is kilo compared to the base unit, what is deci, centi, milli, and micro, all compared to the base unit, and you can convert any of them. So, handouts. The handout that has the balancing equations, the front page, maybe I should have just reordered those, but the very front page is 2 pages of unit conversions. And the answers to those are also posted in Moodle. Okay, so you can find, if you go through, even if you just do half the sheet, practice them, see if you can do them, set them up for a while at least, write it out. Like, just make yourself sit down and write out the steps, because math is a lot like muscle memory. When you do something and you repeat it, you practice it, then it sticks with you. If you do it once or twice and you stop looking at it, then it starts to fade. Just like you go to the gym January 1st and you're like, I'm going to be strong. And you're doing really good. And then February, you're like, I'm really busy. Okay. And then by March, you're like, okay, I'm weak again. Right? It doesn't stick with you if you don't consistently repeat it. So between now and the first exam, try and practice these. Practice them and practice them. Practice those balancing equation problems, even if you're just doing a couple of them a day. Because that way, it's getting more and more familiar. It almost then becomes like, just like muscle memory. Your brain goes, oh yeah, I remember that. Okay, oh yeah, I know how to set this up. It becomes more and more familiar, because this is not something you sit at the dining room table and talk about. Okay? You know, for a lot of your classes, like you talk about psychology classes, you're like, oh, I know this person's like this. Oh, I knew somebody like that. You can kind of like relate to a lot of personality things. You can relate to a lot of those personal experiences, but this isn't always that. Okay. As we get further in the semester, hopefully you will hear things that you were like, oh, I've always wondered about this in nutrition, or this about food, or this about dietary stuff. But this is kind of this math basics. And if you haven't seen it in a while, you really want to try and practice it just to get more familiar. All right. So why are you going to need to do this? I will tell you that in order to continue on, if you're going into nursing, you will actually, one of the first things that you will have is a dosage test. You will have a test specifically on math, specifically about dosages, and dosages almost always require you to do some kind of unit conversion. Okay, so becoming familiar and comfortable with setting things up. Some students use a number line. I will tell you, if you forget 1 unit on your number line, you could end up giving your patients 10 times more or 10 times less or 100 times more or less of some kind of drug that may end up having a life-threatening issue. So in this, a doctor orders 0.25 milligrams of digoxin. So digoxin is consistently given after a heart attack. It helps to slow and steady heart rate. You have a solution. So a solution means it's in what? It's a mixture, and it's probably dissolved in some kind of water. It might be in saline, but odds it's a liquid. Water is going to be like what's dissolving. You have a solution of 0.5 micrograms per milliliters. How much of this would you give? So when you look at this, things you can always think of like, okay, things that I know. So things that I know that I have to give 0.25 milligrams of this med. Okay, don't really care what the med is. It's really the number that I care about. And I know the concentration. So concentration is when you have a medication in a liquid. So I have some sample measured out and dissolved in some volume of liquid. So the concentration is 500 micrograms per milliliter. which means 500 micrograms per 1 milliliter of the solution. Concentration, and I know the amount, the mass that I need to give. So you can take your dose times concentration to figure out we'll set it up this way. When I give this medication, it is a solution, so the amount that I'm going to have to give is going to need to be some kind of volume. Because it's a solution. So my medicine is in a liquid, so I'm going to have to give some kind of volume. And in this case, it's milliliters is what I know my volume is. So I know my volume in milliliters. So that means that I have to end up with milliliters all by itself. So if I took 0.25 milligrams, that's the amount that I have to give, and I want to use this concentration, I want to get rid of milligrams. Think of it almost like a unit conversion. I want to get rid of milligrams and get milliliters as my answer. So I can use this concentration to do that, but I have milligrams as my dose, and my concentration is in what mass? Micrograms. So do you see that milligrams and micrograms are not the same? So I can't use them together. They will not cancel each other. It'd be like talking about pounds and ounces. You have to put them both in the same unit. So I would change the concentration because it's all by itself. So if I changed 0.25 milligrams to micrograms, then I can use micrograms and micrograms, cancel that, and figure out what my dosage is. So, is this one step or two? Two, because I have milligrams and micrograms. So 0.25 milligrams is equal to how many micrograms? So I have times and a line. What goes on the bottom? Milligrams goes on the bottom, grams on the top. I'm going to do the first step. I want to go from milligrams to grams. Milli gets the 1,000. Grams get to 1. Now I got to do a second step, though. So in this one, I'm going to go from grams to micrograms. So micro gets a million. Just make sure. 1, 2, 3, 4, 5, 6. See, I left a 0 out. 6 zeros after that 1. There's a million micro in a base unit, so a million micrograms in the gram. So milligrams to milligrams, grams to grams, those cancel, leaves me with my answer in micrograms. So I'm going to take and multiply 0.25 times a million divided by 1,000. Everything across the top, 0.25 times a million, and then divide by anything in the bottom, so divide it by 1,000, and you get 250. Did everybody get 250? Okay, so now my masses, micrograms and micrograms, are the same. So I can now take 250 micrograms, and I'm going to multiply it times the concentration. So concentration is micrograms per mil. So which unit do I want to put on the bottom? I want them to cancel. Out of this concentration, which unit, micrograms or milliliters, which do I want to put on the bottom? Micrograms. I want to put micrograms on the bottom, and I can put milliliters on the top. That is the solution concentration. I just insert those numbers. So micrograms, there's 500 micrograms in 1 milliliter. This is the concentration of the medicine. So I'm taking the amount I got to give, multiplying it times the concentration of the medicine, but I have to set it up so that the units can cancel. Micrograms and micrograms will cancel this way, and it leaves me with the amount I have to give in milliliters. So 250 divided by 500 would be 0.5. So checking to make sure that units are the same when you have to give dosages, making sure that if you have a medication, so oftentimes you'll have to give things in like milligrams per kilogram of body weight. You got to make sure that you convert the patient from pounds to kilograms. Most beds do that now, which is really nice. Okay, so you just have to hit a button and it automatically switches, but you can use unit conversions to do the same. Same thing in this. If you're giving a liquid and the doctor orders like a mass, then you know that you're going to have to figure out how much of that liquid you've got to give. And it may require that you do a unit conversion to be sure that medication mass and concentration mass are the same before you can go through and get those units to cancel. So we'll practice some of those. In chemistry, because we do so much measuring, significant figures comes into play. So significant figures really matter when you're talking about a measured amount. So if you measure out 12.5 grams, okay, you measured that. So how sure are you of that number? Are you sure about the 1, the 2, the 5? Which numbers are you sure about? That's where significant figures come into play. So if I said, if I have, now it's going to do this. Okay. 12.5 grams. So if I measure out 12.5 grams of sodium chloride, so salt. If I measure out 12.5 grams, then that means that I'm sure of the 1, I'm sure of the 2, and the 5 is the one that I'm kind of uncertain about, but that is sort of like the smallest measured value in that unit. So all of these are considered significant figures. They are all what they call the known digits plus the last one, which is always the estimated. So there would be 3 significant figures in this number. Any number from 1 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, any number other than 0 is always considered a significant figure in a measured value. So it doesn't matter if I have 1,234,567 pennies. How many significant figures would that be? 7. All of those are considered known and measured values. The 7 is probably the only one I might be a little uncertain about, but it's still measured. I counted it, okay? But now, what if I said that I have 1,000,000 pennies? You look in your coin bin and you're like, wow, I think I have 1,000,000 pennies. Is it exactly 1,000,000? That's like an estimated number, right? So it's like, I know there's a lot. It looks like 1,000,000, but I haven't actually measured all of them. So this is with those zeros. Zeros are the challenge when thinking about measured numbers and looking at measured values. Zeros at the end of a number, if there's no decimal place, they are not significant. So that million has how many significant figures? Just 1. So this would be, if I said I got 1,000,000 pennies, this is only 1 significant figure. Same thing if I said that I had 0.00001 grams of salt. Those zeros out front, they call those leading zeros. Zeros out front are really just showing you the size of the number. They are not considered significant. Leading zeros are the zeros out front with a decimal place. They are not significant. Zeros at the end with no decimal place are not significant. So this one, 0.000001 grams of salt, that'd be very, very small. That would also only be 1 significant figure.
But if it was like 0, 1, then it would be like 1, 5.
So there's only 2 times that zeros are significant. Zeros are significant when they're in between. So if you said that I have 1,000,001 pennies, that means that I actually counted out 1,000,001 pennies. So those zeros in between, now they're considered counted. They're measured numbers. So that would be how many significant figures? That'd be 7. So I'd have 7 significant figures in that number. Any zeros in between non-zero numbers are just like a non-zero number. So they're counted numbers. The only other time zeros are significant if there's a decimal and zeros at the end. And it doesn't matter if the zeros are before the decimal or after the decimal. If they're after a number at the end with a decimal anywhere in the number, then they're considered significant. So in this one, if I had 0.01000 grams of salt, how many significant figures in that number? 5. Okay, so the 5 significant figures in that number would be these. There's a decimal, so every 0 at the end and that one in between, those would be considered measured values that would give you 5. Those are the only times zeros are significant. That decimal place could be anywhere. So I could have like 12,000.000, 5 significant figures. There's a decimal place, there's zeros at the end, those count. I could have 0.001200, also 4 significant figures. Those zeros at the end are significant. The ones out front never are, but the ones that are at the end here, this one would be 4. All of those would be, this one would be 5. So any zeros at the end are significant only if there's a decimal place. So it's easiest just to practice these here. So first off, you tell me how many significant figures in that number. 0.120568. 6. And if anybody doesn't understand, just throw a hand up so we can run through them. What about 12,500 liters? 3. Everybody got that? No decimal place, zeros at the end are not significant. What about 4,561.0025 centimeters? 8. All of them. Okay, because those zeros are in between. What about 0.0025896 decigrams? 5. Zeros out front, not significant. Leading zeros never count. 0.004510 kiloliters. 5. Anybody not get that? So remember, zeros at the end after a decimal, those are significant. What about this one? 1, 2, 3, 4, 5, 6, 7. So that's a million. 1 million millimeters. There's a decimal place, so what does that tell you? If there's a decimal place, all the zeros at the end. So this would be like, I measured exactly a million. So that's different than just saying a million. 1, 2, 3, 4, 5, 6. A million millimeters, that would just be 1. There's no decimal place, so those zeros, that's the estimate. I got 1 million pennies. But if I actually counted 1 million pennies, I would put that decimal place at the end to show you. I measured it all the way down to the ones place. But anything at the end with a decimal, so those are at the end of the number. If there's a decimal place, anything at the end would count. So it wouldn't matter. I could put that decimal place anywhere. So I could have 100.123 millimeters. How many would that be? 7. Okay. Decimal place anywhere, anything at the end, before or after the decimal place is considered significant. So what about 9,500.120? All of them. So all of them. So that one would also be a 7. These are only referred to measured numbers. When you do unit conversions, you never round. You never have to worry about that. You just do the unit conversion because unit conversions are considered like standard values when you do a conversion. But if I wanted to round, what is the rule for rounding? If you want to round a number, if it is 5 or greater, that is our rule. 5 or greater, you round the number up. Anything less than 5, you round the number down. Okay? So, if I want to round 0.120568 milligrams to 3 significant figures, when I want to round, start from the left. Find the first 3 significant figures in this answer. So what are the first 3 from the left? The 1, the 2, and the 0. Right? So does everybody see these are the first 3 significant figures? The 0 out front is not. Zeros out front are not significant, so I have to go to the first 3 significant figures in my number. The next number is a 5, so what's that going to do? It's going to round my 0 up. So that's going to be 0.121. I don't drop the decimal place. I don't drop the 0 out front. They're not significant, but they show you the size of the number. What about the next one? So if you had $12,500 and they said, I'm going to round you to 3 significant figures, would you be okay getting $125? No. What do you have to keep? I have to keep those zeros. So I keep the 1, the 2, the 5. The 2 zeros stay because they show the size of the number. But there's only 3 significant figures in that number to begin with, so it wouldn't change the number. All right, 4,561.0025 centimeters. What are the first 3 significant figures you find? The 4, 5, 6. The next number is a 1, so what would that do? Round down. So I'm going to keep the 4, 5, 6, so that 1 becomes a 0. Do I have to keep it? Yes, because see where my decimal is. So I keep the 0 at the end. It's not significant, but it shows me that my number is 4,560, which is rounded from 4,561. The 0 at the end is there to show you the size of the number. It shows you where the decimal place should be. You don't include the decimal place because of those. That's 0 is not a significant figure. What about the next one? 0.0025896. 3 significant figures are the 2, 5, 8. So then I know the 9 and the 6 are the things that I have to round. What is that going to round? Up or down? Up. So my 8's going to become a 9. So in this case, do I keep the zeros out front? Yes, because it shows the size of the number. 2, 5, but my 8 becomes a 9. 0.004510. Just drop the 2 zeros at the end, she said. So here's 451. Those are my first 3 significant figures. The zeros out front don't count as significant figures. If I'm going to round, then that means those zeros end up getting rounded off. So my number, 0.00451. This one, I won't ask you to round something like that. Because what you would have to do is you'd have to put 1, 2, 3, 4, 5, 6. And I'd have to have that. If you remember that from math. But I won't ask you to round one of those. Do you remember that the line across shows that those were significant figures? But that's fine. This is another one that gets a little hairy sometimes. Because 9,500.120, what's your first 3 significant figures? The 950. Okay, so when I go to do this, that 0 stays a 0, and then students look at this and go, but that looks just like 2 significant figures. Agree? 9,500? Doesn't it look like it's only 2 significant figures because there's no decimal place? So again, I try to avoid this, but in math, you would actually put a line over that 1 because it's significant. We don't really come into play with that. I'd be fine with just 9,500 because at least it's there. All right. Why do you have to know this? Why do I have to know this? So if you have measured values in a math problem, your answer cannot have any more significant figures than the numbers in the problem. This is the case with multiplication and division. So, for example, if I'm multiplying 12.3 centimeters times 2, somethings, no units. If I get an answer, my measured numbers, 12.3 and 2, how many significant figures in 12.3? 3, right? So everybody agrees there's 3 significant figures in 12.3, but how many significant figures in my 2? It's only 1. So that means whatever this answer is, I can only have 1 significant figure in my answer. And so just doing the math for this one, so this would be 4, and that would be 2. So it'd be 24.6. I'd have to round this to 1 significant figure. So what would my answer be? No, 25 would have 2 significant figures. If I only want 1 significant figure, it would be 20. First 1 significant figure, so this would end up rounding to 20. So if you have measured values in your problem, when you get your answer, and you will see this a lot, you will see all 10 digits in your calculator. And so students are always like, I don't know, I'll just round it to a whole number. They just like randomly pick a number. There actually is specifically, you have to use specifics in doing this. So let's look at the first one. We're not going to do the plus and minus. We'll go back and do that next time, okay? I just want to do the multiplication and division for you. So in this one, when multiplying and dividing, first do the math. So if you take 0.120 times 2.782, what did you get for an answer? Yeah, I can't write it down. So if I take 0.120 and I multiply it times 2.782, I get 0.33384. How many significant figures is that? 5. Okay, well, how many significant figures in 0.120? 3, right? The 0 out front doesn't count. 0 at the end counts because there's a decimal. How many significant figures in 2.782? 4. So that means, so I have 1 with 3, 1 with 4. I've got to round my answer to 3. So you look at your answer, underline the first 3 significant figures you get to. Remember, the 0 doesn't count out front, but the 333. So I know that that next one, the next one I'm going to have to round. So 384. So I'm going to stay to here. That means I'm going to have to round. That's an 8, so what's it going to do? Round up. So my answer would be 0.334. Least. Your answer needs to be rounded to the number with the least significant figures in the problem. So same thing with this one. So if you take 12,500 divided by 3.7, I have like the entire screen. Okay, so if you look at it, it's 3378.378378. And so I see this when you do math, you always end up like, inevitably, you end up with like all these numbers on your calculator. You're like, So how do I know what to round that to? Look at the problem. 12,500, how many significant figures? 3. 0 at the end, zeros at the end don't count because there's no decimal. But then 3.7 has 2. So that tells me my answer needs to be rounded to just 2. So look at your question. First 2 significant figures are the 2 3s, okay, starting from the left. So that means that 7, what happens? It's going to round up. And so what's my answer going to be? 3,000, what? 400. So those zeros at the end show me how big the number is. Because see how the number was 3,378 point blah, 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 blah. Okay, so I do have to add those zeros at the end to show the size of the number. The zeros at the end are not significant because there's no decimal place, but that gives me 2 significant figures in my problem. So we will actually do, like those ones are ones you can practice. There is a significant figures and rounding dynamic study module. So one, just helping practice like what is the tens place, the ones place, the hundredths place, like going back over some of that in terms of decimals, but also picking out significant figures and then working on this rounding. So we will pick this up on Thursday, finish this and the rest of chapter 1 on Thursday.